Okay, this next problem we're going to do is on Taylor series, and particularly integrating Taylor series, so doing some operations with Taylor series. And in doing that, we're going to have to focus on the radius of convergence.
At the Taylor series for this function. So when you're asked to find a Taylor series of a function that isn't something that you know, it's just going to be, we're going to get it from a Taylor series of a function that we do know. So for example, we know that the function 1 over 1 minus x is equal to the sum from k equals 0 to infinity of x to the k, right? And then we also know that the function e to the x is the sum from k equals 0 to infinity of x to the k over k factorial. Over k factorial. So we're going to use these two functions to find the function that we actually want to find. So first, let's just look at it each part at a time. So the way I'm going to work with this is I'm first going to look at 1 over 5 minus 6x. And I want this to look like, so what I'm going to try to do is I want this to look like 1 over 1 minus something. Okay, so the way I'm going to do that is I'm going to bring out a 5 from everything. So what I mean is bring out a 5 on the bottom, so we have 5, and this becomes a 6x over 5. Right? So now, what do I have? Well, now, if I write this as 1 over 5 times 1 over 1 minus u, where u is equal to 6x over 5, then I have 1 over 5 minus 6x is equal to 1 over 5 times the sum from k equals 0 to infinity. And I'm going to use this result here, right? I'm just going to, instead of x, I'm going to have a u. So this is u to the k, or this is equal to 1 over 5, and now I can plug back in for what u actually is, and I find k equals 0 to infinity 6x over 5 to the k. Now I can simplify this a little bit more. So what I want to do is I really want this to be one sum. So I'm going to bring this guy inside, and I have the sum from k equals 0 to infinity. I have 6 to the k, x to the k, over 5 to the k, times 5, so that's 5 to the k plus 1. And my k's don't show up very good on here, but these are all k's. Okay, so this is equal to 1 over 5 minus x, or 6x. So that's one part of my function. But I also want this other part of my function, right? I want this term, e to the 2x. So to find e to the 2x in terms of Taylor series, I'm going to do the same sort of thing. I'm going to say e to the 2x is equal to e to the v, I'm going to call it now. And e to the v, well, we just said above that e to the x is the sum from k equals 0 to infinity here, x to the k over k factorial. So this is v to the k over k factorial. Okay, so now we want to combine these two things. We want to add these two Taylor series. We know that 1 over 5 minus 6x plus e to the 2x is equal to, well, we have the first part, k equals 0 to infinity, and we have 6k, 6 to the k, x to the k, over 5 to the k plus 1, plus k equals 0 to infinity. If we realize that this v to the k is actually 2x. This is going to be k equals 0 to infinity. 2x to the k over k factorial. Here we have the same thing, 2x to the k over k factorial. Be careful, because these are individual things, right? They're not necessarily added together yet. So the only way we can add them together is if we're within the radius convergence. So we can only add what we call term by term if we are within the radius of convergence. Okay, so I'm going to write convergence conv. Okay. So now we need to look at the radius of convergence. So the radius of convergence for the first function. The way we find the radius of convergence for two functions together is we take the smaller of the two radiuses of convergence, radii of convergence. So radius of convergence of first function, well, we know, we go back to this function. Well, this right here only converges for absolute value of x less than 1. So let's go ahead and look at here. So now we have, what we end up having is this sort of 6x to the 5, 6 times x to the 5, 6 times x over 5 to the k. So what we need is absolute value of 6x over 5 less than 1. Now, obviously, we have this 1 over 5 up front, but it doesn't matter, right? Because this is just multiplying by a constant. This is only going to converge when this thing is small enough. So what we can say is that this is when absolute value of x is less than 5 over 6. And that's just multiplying through by 5/6, because that's a positive number. Okay, so the first one only converges for x less than 5/6. Now, when does the second one converge? This one converges for all x. So this is all x. This thing always converges. So this, because the second one, so we're going to say second converges for all x. So the overall radius convergence, we'll take the smaller of the two. The overall radius convergence is, well, it's just going to be this thing, right? So we need absolute value of x less than 5 over 6, which we notice is less than 1. Okay. Okay, so in that so whenever we're in that regime, then we know that 1 over 5 minus 6x plus e to the 2x, now we can bring both inside the same sum. But you can only do that if you're within the radius of convergence. So now we have this 6 to the k, x to the k, over 5 over 5 to the k plus 1. And this is all within one bracket, and then plus, well, we have this 2x to the k, so 2 to the k, x to the k over k factorial. Okay, so we can rewrite this. For a Taylor series, you always want to write it as some coefficient. So this is going to be x to the k over 5 to the k plus 1 plus 2 to the k over k factorial. This is going to be my coefficient times x to the k. So if you've seen in our notation, we sometimes call this a k. So this is the kth, this is constant. It's a constant with respect to x, but as k changes a different value. So now we want to integrate this thing, right? This is our goal, is we want to integrate this Taylor series term by term. So, and we're going to integrate from -1 to 1. So what that means is that we're going to do k equals 0 to infinity, integral from -1 to 1. So now we're going to sum over all the stuff. We have one big parenthesis out here, and then we're going to just do each term, and this is 6k. It's going to be a little bit messy. 6k over 5 to the k plus 1 plus 2 to the k over k factorial x to the k dx, right? And of course this whole thing is constant, right, with respect to x, so let's bring it out. And what we have out here is this sum still, k equals 0 to infinity, 6 to the k over 5 to the k plus 1 plus 2 to the k over k factorial, and then we just have integral -1 to 1 x to the k dx. Okay, so now we can just integrate this thing. That's the beauty of this. And we're really going to sum over all of this still. This is still one big sum, right? Because this depends on k. You can't just bring it out of the sum. Okay, so we're almost there. We have k equals 0 to infinity. This constant still. I'm going to call this constant a to the k, ak. I've already defined it above. And then I have times, well, this is just going to be x to the k plus 1 over k plus 1 from -1 to 1. K equals 0 to infinity, ak, which I've defined above again. And this is going to be, well, I have 1 over k plus 1 plus, well, now this is going to be -1 to the k plus 1. So this is going to be either plus or -1 depending on k, just like we talked about in the last problem, to the k plus 1. Okay, so we see this is going to depend on what the value of k is. Well, this thing is going to depend on what the value of k is. Okay, and so we have some number. And then what we're going to look at is, so we can write this out exactly. We have something, k equals 0 to infinity, and what did we have here? We had 6 to the k over 5 to the k plus 1 plus, whoops, is it 2 to the k? Yep. 2 to the k over k factorial, and then I have 1 over k plus 1, and then I have 1 plus, I'm going to write this as 1 minus, I'm going to write this as 1 plus -1 to the k plus 1. Okay, and now the question is this the same number as this? So now we're just going to integrate this thing actually. So now we're going to actually integrate from -1 to 1 f of x dx. So we're going to do a comparison, and we have -1 to 1 f of x dx. Well, this is just -1 to 1, and we have 1 over 5 minus 6x plus e to the 2x dx. And this is equal to, well, we could do it each term by term, right? I'm going to write this as 1 over 5, 1 minus 6 over 5 to the x, 1 over 6 minus 5x dx, plus integral -1 to 1 e to the 2x dx, which is going to be, we'll have 1/5 here, and then I'm going to have, well, I'm going to have 5 over 6 ln of 1 minus 6 over 5 to the x, 6 over 5x, from minus 1 to 1. So make sure you understand why that is, right? Actually, we end up getting a minus sign here, so I almost messed that up. But if you take the derivative of the inside, then you get the 6 over 5, which cancels out. And then we have plus, we have e to the 2x, so this becomes a 1/2 e to the 2x from minus 1 to 1. So I'm going to cancel these guys out, and this becomes a minus 1 over 6. And I have ln of 1 minus 6 over 5 minus ln of 1 plus 6 over 5 plus 1/2 e to the 2 plus, or minus e to the minus 2. Well, we can simplify this a little bit more. This becomes a minus 1 over 6 ln of, well, 1 minus 6 over 5 is 5 over 5 minus 6 over 5, so that's minus 1 over 5 minus ln of, well, 5 over 5 plus 6 over 5 is 11 over 5, and then we have plus 1/2 e to the 2 minus e to the minus 2. Now, you should be worried. This, we can't do a log of a negative number, right? So this is a problem. And this is why this question asks, explain why this does not work after calculating the integral. Okay, so we just figured out we cannot do this integral. Okay, and that's because it doesn't converge. So we talked about the convergence a little bit in Math 125, but now we talk about this. But it looks strange, right? We just found this series. They should be the same, right? No. However, if you notice, we can only integrate if we're within the radius of convergence. So this integral does not converge. Also, the sum in the first part also does not converge. Okay, so the moral of this problem is only integrate in the radius of convergence. Okay, so, well, what went wrong here? Look, we just said up here when we calculated this series that this is our radius of convergence. But, well, minus 1 to 1 is outside of that radius of convergence, right? 1 is greater than 5 over 6, and minus 1 is less than minus 5 over 6. So, absolute value of 5 over 6 is less than, is less than 1. So we can only integrate if we're integrating for something inside minus 1 to 1. So this stuff outside of minus 1 to 1 doesn't work. So that's why this doesn't work. So now let's look at this function. Now we're within minus 1 to 1, so we should be able to integrate this term by term. So let's say b, we have minus 1 to, or minus 1/2 to 1/2 f of x dx. Well, I'm going to write this in terms of my Taylor series, so I have minus 1/2 to 1/2. I have the sum from k equals 0 to infinity, and I have, what was my Taylor series? 6 to the k over 5 to the k plus 1, over 5 to the k plus 1, plus 2 to the k over k factorial, x to the k, and this is all going to be within one big bracket, dx. Okay, and now, this is the important part. Because we're within the radius of convergence, we could bring this integral inside. You can only do that if you're within the radius of convergence. So now, we have the sum k equals 0 to infinity is minus 1/2 to 1/2. We have the sum where this coefficient, which I'm going to call a to the k, x to the k dx. This a to the k now I can bring out and put it here, right? So this is going to be the sum from k equals 0 to infinity, a k, which I'm not going to keep writing, and we just integrate x to the k, so we have x to the k plus 1 over k plus 1, minus 1 to 1. But now, if you notice, this is, or sorry, minus 1/2 to 1/2, this is within our radius of convergence, right? Because 1/2 is less than 5/6. So now we can write this as k equals 0 to infinity, ak over k plus 1, and we have 1/2 to the k plus 1 minus 1 to the k plus 1, 1/2 to the k plus 1. And I write it like this because if you notice, this is equal to minus 1/2 to the k plus 1. So we talked a little bit about that in the last video. So I like to write it like this because then I can go ahead and write, well, this is k equals 0 to infinity, ak over k plus 1, and then I have 1/2 to the k plus 1, 1 minus 1 to the k plus 1. Okay, and this is the preferred way to write it. You've already defined your ak above, somewhere up here, so that's fine. And this works, actually. This is the correct answer because it was all within the radius of convergence.